Assalamu alaikum. In the past few months, we've been together in a journey trying to discover the soil. We have seen the definition of the soil, the importance of the soil, the functions of the soil, and we have seen how the soil is formed and the weathering process and all of the marvelous things. And we have also discovered the physics of the soil and unraveled the secrets there. But today, it's a new dimensions. It's a new journey that we want to unravel the secrets of the chemistry part. So let's do it together. Through today's lecture, we're going to learn a lot of amazing, fascinating things. For example, we're going to see how the sizes of the soil particles are very important for the chemistry aspects of the soil. We're going to see whether colloid means clay or also something else. We're going to see how the clay minerals as a mineral are formed and what is exactly on these minerals as a building blocks. And finally, we're gonna see different types of clay and the differences between them, and we're gonna understand a lot of more interesting things about the soil. So without further ado, let's begin. All right, so I want you at the beginning to stretch your mind and think a little bit with me. Open your eye and sharpen them and look at the picture that you have. Look at it very well. So this is basically a case study and I want you to answer some questions. So there was a wastewater which was discharged from a factory, as you can see from the pipe, and this wastewater is discharged in two different soils, soil A and soil B. After some time, of course, the chemicals or the wastewater arrive to the groundwater, reach already to the groundwater. Now look at the picture down and look at it very well and tell me under which condition the groundwater is contaminated. Then what would be the possible texture of the soil where groundwater got contaminated? And third, what are the possible explanations that makes the soil able to filter the contaminant? Now, spend some time, focus and look everything on the picture, focus and then try to answer these questions. Then we're going to do it together. All right, so here's your moment. Alright, I think this might be enough time for you. If it is not enough, just try to pause and then think more about it. But let's do it now together and let's analyze it. So first of all, if we want to answer the first question, and which soil is groundwater contaminated, we have clues on the picture. And number one, look at soil A and look at soil B and look at the color of the leachate, because the color of the leachate would indicate the quality of the water. So that was the first hint. As you can see, the wastewater is like very dark and the leachate color in A was also dark, whereas in B it turns like blue, like the groundwater color. So it means that soil A is the soil where groundwater got contaminated. Now to answer the second question, what would be the possible texture of the soil A? Now we have to think why the water passed quickly, why the wastewater didn't get cleaned up. And that might be already related to some of the things that we have taken in the physics. Whether the absorption effect here, whether the surface area is important here, whether the particle size are important here, and so many other aspects that you might think of. But one of the possible things that the soil texture, that's what we want to know. So we know that soil texture, for example, if we compare sand and clay, we know that sand, the water can pass very quickly because it has larger pores, and we knew a little bit from the physics that it does not have that some charges, and it has small surface area, so it cannot absorb things and retain it. And that a possible explanation why the groundwater with soil A got contaminated. Now to answer the third question, what are the possible explanations that makes, for example, soil be able to filter the water? Now let's think again. The same concepts that we used to analyze the second question can be used to analyze the third question. So if you have a larger surface area, if you have a fine soil with a larger surface area, with some charges, with smaller pore sizes, that all can affect the movement of wastewater, making it slow a little bit, retain the chemicals on the soil, and therefore filter the contaminant. So these are like opening questions that would help you to understand a lot of interesting things about the chemistry part of the soil. So the ability of soil to control the spread of contaminants and to filter the contamination is basically the same reason why the soil is able to hold nutrient, water, and also provide a good environment for many biological and chemical activities. And this things also is related very much to the particle size and the surface area. We knew from our physics background about the soil that the smaller the particle size, the higher the surface area that it would get. And a higher surface area means more space for holding and retaining things on the soil. And we knew that the surface area of clay is much higher than that of the sand. And therefore, if you have more clay in your textural class, more percentage of clay, it means that you are increasing the chance for holding, increasing the surface area, and therefore holding more nutrient, water, or controlling contaminants. Now I want you to keep in mind that when we mention the term clay, it basically means different things. We have already seen that clay is the particle size of a less than 0.002 millimeter in diameter. And we have seen that clay is a textural class, as you see in the triangle. But today, and from onward, we're gonna look at clay at mineral as a group of minerals with a different chemical composition, and we're gonna discover the differences there. So for example, look at the third picture here, A, B, C, D, E, F, and you can see different structures. I would shock you if I say that these are basically different clays minerals. Now when you focus on them, you would find that they look completely different. I mean, the structure of them is different. Some of them are like in the book sheets, and some of them looks like sponge or like round in shape. Now, why they are different? And does it really means that when they are different in shape that they have a different composition? I mean, chemical composition? And does that going to affect the absorption of nutrient, chemicals, and water, and also the behaviors? Colloids and clay, are they the same or there is a different story? Well, let's first try to understand what colloids mean. So colloids are extremely small and highly reactive organic, make it bold, and inorganic particles. Now pay attention to this, organic or inorganic particles with electrically charged surface. They are basically less than 2 micrometer or less than 0.002 millimeter in diameter. They're very small to be seen by the naked eye, and you need to use a microscope to see them. Now the colloids have a very high surface area per unit mass. So for example, the colloid will have a surface area up to 10 to 800 meters square per gram, whereas if you just look at the sand, it's just 1 gram would have a surface area of about 0.1 meters square, and 1 gram of salt would have about 1 meter square per area. So it means that it has a large surface area with charges, so they have the ability to hold water, nutrients, and they provide the places for a lot of chemical reactions. Now, Based on these informations, is colloid means only clay? I mean, we have seen that from the previous slide, that clays, that many of the properties of the clay fits very well in the definition of colloid. It means that clay is really a colloid. But if we go back up and focus on organic and inorganic, it makes that there are other things that we have not discussed about colloid. So colloids, it includes clays, it includes also aluminum and iron oxide minerals, and it also includes the organic minerals. But all of these things has to be very, very small up to these specifications in terms of the sizes and the surface area and other things. So now, why the colloids types and including the clays are able to retain the nutrient water and provide these places for the chemical reactions and controlling contaminants? Why this? Yes, true that they have a very high surface area, but does it always mean that a higher surface area means you would be able to absorb things? I mean, keep in mind these things, that the surface area is not the only reason why these clays and colloids are able to retain these things. But because colloids and particularly clay, they have also some charges. That's why they are able to retain. Now the surface area provide a lot of space that you can accommodate things in the soil, but with the charges, it means that you can also not only accommodate them, but retain them and hold them in place. I'm sure that every one of you got excited and wanted to know, where does the clay got the charges and how these charges are basically formed? And to be able to answer this question, we have to look back at the history of the formation of the clay. Now I think you remember this table, and you remember that we have two different types of minerals, primary and secondary minerals. And we have seen that different barren materials with different chemical compositions, when they are subjected to weathering, physical and chemical weathering, they will be disintegrated into smaller particles, and that can reach to the clay size. And not only that, the chemical weathering would help to change the chemical composition, and that's why you might end up with a secondary mineral type that are very stable. Among the list of the secondary minerals, you would see clay minerals. So clay minerals are basically at the end of the formation of the soil, because they are the smallest size of the particles, and also they have a secondary types of minerals. Of course, that when you look at the primary minerals, you have different, like simple silicate, amorphil, pyroxene, quartz, feldspar, and others, as you have seen in the table. But the secondary minerals constitute of oxides like iron and manganese oxide, aluminum oxide, carbonate, magnesium, and calcium carbonate, and also constitute of the clay silicate minerals, including smectite, vermiculite, illite, chlorite, and kaolinite. Now, don't bother yourself with these. We're gonna learn more about these types of silicates, clays, in the coming. As we have seen in the table, that the origin of the clay, that when you look at the clay, you would see that mostly they are secondary minerals formed from the dissolution or alteration of the primary minerals. Not only that, they are basically the product of the environment which we were formed in the past or in the... Something else also very important is to look at the element at the earth crust. And you remember that in the element of the earth crust, oxygen, silicon, and aluminum are very predominant there. There are also other types of minerals, but they are like less dominant, and they are found only in some spaces. However, the three things that I want you to keep in mind, that silicon and aluminum, since they are dominantly present on the earth crust, and since they are predominant in the soil, we would expect them to find them even in the building blocks of clay. Now let's dive deep inside the atomic structure of the clay and look at it, how it's really formed internally. So since we already mentioned that silicon is predominant and aluminum as well, we would find them exist at the central structure, atomic structure of the clay. And they are basically two building blocks of the clay in the atomic structure. We have the first one, which is called tetrahedron. Now tetrahedron is from its name. Tetra means four sides. And tetrahedron in the clay, it's basically you have a silicon atom at the center and surrounded by four oxygen atoms structured and distributed as a pyramid shape. Now, why four oxygen atoms? It's because that silicon is 4+, and therefore to be able to satisfy it you need four oxygen atoms. Silicon are positive and oxygen are negative, and that's why they will be bind together to form a tetrahedron. So a tetrahedron in a simple way looks like a pyramid, and it consists of silicon at the center and four oxygen atoms. The second building block of clay is octahedron. Now from the term octa means 8 sides. The octahedron consists of two aluminum atoms at the center, and they are attached basically to 6 oxygen atoms. We know that each aluminum is 3+, and therefore it needs 3 oxygen atoms. So in total you have 2 aluminum at the center and 6 oxygen at the sides. And they are basically arranged in a shape like two pyramids put together like a side from the base. And if you count the faces, you would find that in total you must have 8 sides, counting also the bases of these two pyramids. In some conditions, instead of oxygen, you might replace it with hydroxide, OH. Now when you put tetrahedrons together, bind it to each other, they will form and build a tetrahedral sheet. And the same things for the octahedrons. When you put them together, they build and form octahedral sheets. And when you put tetrahedral and octahedral sheets together, you're basically now building a layer. And these layers are held to each other by bonds, by chemical bonds. Now, let's stop for a moment and go back to look at from where we started. We started by looking at the atomic structure from very, very small, tiny details. And we have seen the difference between tetrahedron and octahedron. And then we have moved to the sheet level. When you put tetrahedrons together, you form a tetrahedral sheet. And when you put octahedrons together, you form an octahedral sheet. And now we are moving to a larger scale, that you are trying to put different sheets together, a tetrahedral sheets with octahedral sheets, and you will build a layer. And when you put then layers with layers and bind them with bonds, you are building already the clay. And we have different things of clays. For example, if you look at the picture down, you see at Kaolinite, right? The one which starts with K, Kaolinite. The picture of Kaolinite looks like sheets, like a book sheets. And in the same picture you see elite or smectite, and it looks completely different. If you look at the second picture to the right, you would see chlorite. Now all of these are different clay types. It means that they have a different structure and combinations of the tetrahedral octahedral layers. If you look at Kaolinite, for example, up here, you would see that it is considered as 1-to-1 clay mineral. Why? Because 1-to-1 means that you have one tetrahedral sheets and another octahedral sheets, 1-to-1, and they will form a layer called TO, 1-to-1. And then you have another TO, which is another layer, and another TO, which is another layer. And all of these layers forms Kaolinite. If you look at montmorillonite, or it is the same as smectite, it's basically the same type, the same name, okay? If you look at them, at montmorillonite, you would find that it is considered as 2-to-1 clay. What does it mean? It means that if you look at the structural layers, you would find that it is basically formed from 2 tetrahedral sheets with octahedral sheets. That's why it is basically written as 2-to-1, T-O-T, and then another layer, T-O-T, and bind it to another layer, T-O-T, and so on, and then you're building this type of clay mineral. Now, let's go and to see more examples to get this picture very. To help you understand what I meant by building clays, let's look at the simple example here. Building a house, okay? You look at the picture and you would see that to build a house, you need the small things. You need the bricks. And when you put the bricks together, you are basically forming a wall. And by having different combinations of walls, whether you make them in a rectangle or different shapes, you bind them together by cement, you are already building a house. You would see now, because you have put different arrangements of wall, you have different types of houses. You have, for example, this house, the yellow one here, different in size and different in the structure. Then the second 2 floors here, the second picture. Then the third picture here, which is basically with more floors, like 5 or 6 floors. Then the fourth picture. All of these houses looks differently because you have put the combination of walls at a different arrangement. Now this is exactly the same thing like what's happening with clay. So you have the tetrahedron and the octahedrons, which are basically like the bricks. When you put the tetrahedrons together and octahedrons together, you are forming sheets. A tetrahedral sheet and an octahedral sheet. But then when you put these sheets together, like either as TO 1-to-1 and then another TO and TO, or from putting a T layer, then T sheet, then O, then T, TOT, TOT, you are forming different types of clay. Exactly like what you see in the picture. We have different names and different arrangement and structure. But in all of these, in all of the houses, you need blocks, bricks, you need the walls. When you put them together, put the bricks together, they form a wall. And when you arrange them, you will find, or you will form different house structures. And the same things for clay. It is essential in all clay types, you must have these atomic structure. You must have the tetrahedrons and the octahedrons. You must then build the tetrahedral and octahedral sheets. But what differ between them is how you arrange these tetrahedral and octahedral layers, and what is exactly between, or what binds these layers. Alright, so I think we are going gradually and we are getting to know more about these clays minerals. So one of the most important clays minerals, famous, commonly found, are what they call the crystalline layer silicates. And as we said, that this basically forms from different tetrahedral and octahedral sheets, and when you put these tetrahedral and octahedral sheets, depending on the numbers, you would form layers. If you put one tetrahedral sheets and an octahedral sheets, you would form 1-to-1 clay layer, 1-to-1 layer, which is basically TO. And when you put 2 tetrahedron and an octahedral sheets, you would form TOT layer. And when you put these layers together in a repeated sequence, then you would form different clays like montmorillonite, kaolinite, illite, and kaolinite. And if you started just with the kaolinite, you would see how these TO are repeated to each other. For example, you would see at the top here that the pyramid shape, which is basically the tetrahedral sheets, and then it is attached to
an octahedral sheet. So this is 1TO. Basically what links what bind the tetrahedral sheets with the octahedral sheets are electron sharing. Then you have another layer which is TO also. So the first layer here and the second layer of TO are binded together, as you see here from the structure, by a hydrogen bond. Why? Because if you look at the end of the top TO layer, at the end you have the octahedrals, and in the octahedrals in this case you have OH, so it's -1 OH. And then at the top here you have what? You have at the top of the second layer you have the tetrahedron, and the tetrahedron you have oxygen. So now when you bind oxygen with hydroxide, they will be binded by the hydrogen bonds, and this hydrogen bond is very strong. So you see now how TO and another layer of TO are binded together, and they will form Kaolinite. And this is just an example of just 2 layers, but the Kaolinite basically consists of so many layers repeated in a repeated sequence of TO, 1 layer binded with a hydrogen bond with another TO and another TO and another TO, and so on and so on and so on. By giving you this example, you would be able to visualize the differences between the different types of clay minerals that we mentioned here. So I want you at the beginning to go down in the sketch and look at the names and the sequence of layers. So you would see that Kaolinite is 1:1 clay. Then smectite is 2:1. Vermiculite is 2:1. Fine micrograde is 2:1, and chlorite is also 2:1. Now, if you just focus at Kaolinite and go up and look at the sketch, you would find that we call it 1:1 because it consists of tetrahedral sheets and octahedral sheets, and will be 1 layer. Then you have tetrahedral sheet, octahedral sheet to form the second layer, and so on in a repeated sequence. And as you see here that the top layer, TO, basically the end of it is you have octahedral sheets. However, the second layer start here in the arrangement because it's TO, then you have at the top here tetrahedral sheets. And you know that in the octahedral you have hydroxide, OH, and the tetrahedral you have O. That's why they are binded by hydrogen bonds. If you come and to look at this, all the other examples, the other clay examples are all of them 2:1. It means that each layer of these types are basically consist of TOT, tetrahedral sheet, octahedral sheet, tetrahedral sheet, and this is 1 layer. Then you have another TOT, which form another layer, and so on in a repeated sequence. If you look at smectite, you would find that in smectite, you have a big space between the 2 layers, TOT layer and another TOT layer. Why? Because the end of the first layer here is tetrahedral sheets, which is ended with oxygen. And the second layer here start with T, which is also having oxygen. Now you know that oxygen with oxygen negative, and they repel. Now this type of clay is expanding. Why? Because the bond here that links the first layer and the second layer is very weak. And because now we call it expanding, it means that if you add water to it, it will swell, it will expand. Why? Because the water can get into the interspace between the layers, and there is nothing that can hold it. So when water is there, it can absorb it and swell, and when water evaporates and goes out, what will happen to this space? It will shrink. Whereas in the Kaolinite condition, it does not swell. Why? Because of the hydrogen bond. You know it's very strong, and even water cannot go there inside and expand it, so it doesn't absorb that much water as compared to smectite, or what we call it also montmorillonite. Now if you go to the second example of 221, which is the vermiculite, also you have TOT as a layer and then another TOT, but the difference between them, why we call it, it's like having some swelling, because if you look at the interspace between the layers, you would have water molecules plus magnesium and other ions. So these are forming a bonds, and this bond is relatively weaker than the hydrogen bond, but it is better. You have bond, you have a stronger bond than the condition of smectite. That's why when water tries to come, it only allows for some expansion, but not as the condition for smectite. When you go to look at the fine grain, again it's the same thing. TOT as a layer and then another TOT as a layer. But in the interspace you have, you have like a balls. These are basically the potassium. Now the potassium is positive, okay? And you know that the T and the T in the first layer and the second layer here are negative. So that's why they are now, the potassium will bind them together in a stronger bonding than the condition of vermiculite. That's why it is basically a non-expanding clay. Because of this bond, the interspace cannot allow water to get in and create the expansion. And if you look at the other type of 221, which is chlorite, the same thing. We call it a non-expanding because you have hydroxide sheet in the interspace between the TOT layer and the other TOT layer. So that's why we have some of the clays are expanding and some of them are non-expanding. But you have seen now always 1-to-1 like Kaolinite is non-expanding because of the hydrogen bond in the interspace between the TO and the TO layer. Whereas for the 2-to-1 clays, you have some of them are expanding to different degrees, while others are non-expanding depending on what is in the interspace between the layers and what kind of bonds exist there. Like smectite and vermiculite, the bonds are weaker, that's why they are expanding, whereas in the condition of fine mica and chlorite, the bonds are stronger, and that's why they are not expanding. Here is an example that illustrates to you the difference between expansion, when we say expansion, between Kaolinite and montmorillonite, or it is the same as smectite. So now, if you look at these two examples, you would see you have four graduated cylinders filled with soil. The first two are for Kaolinite soil. The first one when the condition was dry before adding water, but later on you added water to the Kaolinite. And what you see now here, that the soil get even compacted. It did not absorb the water. If you move to see the montmorillonite condition, when the soil was dry, you see how was the volume of the soil, and you added the same amount of water that you added to Kaolinite soil. But what happened when it is wet? It absorbs all of that water, and because there is a very weak bond there between the interlayer space, and we know that montmorillonite, or what we call it also as smectite, is a maximum swelling clay. If you go back to the previous slide, that's why it is expanded. It almost absorbed all the water, and this has an implication. That's why you would find that we should use these different clays in a different purposes, and it can create like advantages and disadvantages. So if you look at the Kaolinite, for example, you will find, because it is a non-expanding type of clay because of the hydrogen bonds, it has a properties like less plasticity, less thickness, less cohesion, and does not crack. And because of all of these things, it is a good clay minerals that can be used for construction and for many other purposes. That's why, for example, you find in India and in many other countries, they create bricks with these types of of clays. They create, like in the ancient times of the Chinese, they also have created the pottery and the bricklin. And in Oman we have created also the pottery, like jahla that you see. So the jahla is basically made of a clay type which is kaolinite. Why? Because now when you add water or when rains fall to these structures, to the bricks and the building, it will not absorb water and hence it will not increase in size and it will not crack. The same conditions for the khazafiyat, the bricklin and the pottery, fakhariyat. When you add water to them or tea, they will not absorb that water and therefore they will not expand. And when they dry, nothing would change in their size because they does not absorb water. The condition is different, however, for montmorillonite or smectite, because it is an expanding clay, and because of the weak bonds that link the TOT layer and the other TOT layer, it basically absorbs water, and this is makes it more plastic, more thickness. If you put it in your finger, it's sticky and more cohesive. That's why it is not recommended to use it for construction. If you have this soil in a land, don't build on it. Why? Because if rain happens or leakage happens, it absorbs the water and then it expands. But then when things try to dry, it starts to get what? It contrasts. And because of this movement with drying and wetting, it creates cracks and it creates the technical problems, the geotechnical problems, as you see down in the pictures. The buildings collapse and fall, things are moving. But the advantage of it, that yes, it can absorb water, it means it can absorb also chemicals. That's why this type of clay can be used as an absorbent of chemicals, or it can be used in the engineering applications, in the treatment to absorb the contaminants and so on. So keep in mind these. I guess this is enough for today's lecture. I hope that you enjoyed the journey with the chemistry. It's very easy. Just focus, start from a simple way, from thinking about the atomic structure all the way to forming the layers with the different sequence of layers, and depending on what is exactly on that layer, you form different types of clay. And these different types of clays have different shapes, as you see in the picture here again, and they have completely different chemical properties and physical. It even affects the physical properties like the cohesion, plasticity, and eventually it affects the use. So thank you very much and have a good day.